Earth observation satellites * why Earth observation matters, 0 o'clock to 3 o'clock * welcome. This is a journey across the skies, a tour of the satellites that watch, measure, and help us understand our home planet. Over the next 50 minutes, we'll explore some of the most important Earth observation missions in orbit today: Landsat 8 and 9, the European Space Agency's Sentinel family, Sentinel-1, Sentinel-2, Sentinel-3, NASA's Terra, and India's Cartosat 2 series. We'll look at what each satellite does, how they collect their data, the science and services they enable, and real-world examples of how their images are used, from monitoring crops and mapping cities to tracking wildfires and following coastal change. How Earth observation satellites work: 3 o'clock to 7 o'clock * at their simplest. Earth observation satellites carry instruments that measure electromagnetic energy, light, reflected or emitted by Earth's surface and atmosphere. Instruments can be optical cameras that capture visible and infrared light, radar sensors that actively ping the ground with microwaves, or radiometers that measure thermal emission. Each sensor type reveals different information. Optical multispectral images, like those on Landsat and Sentinel-2, split reflected sunlight into bands: blue, green, red, and multiple near-infrared and shortwave infrared channels. These bands allow us to detect vegetation, health, water, soil, and man-made materials. Radar instruments, like Sentinel-1's synthetic aperture radar, are active sensors. They work day and night and through clouds because they use their own microwave pulses and measure the echo. Thermal sensors measure heat, which is useful for fire detection, sea surface temperature, and surface energy studies. Satellites differ in 3 key ways: spatial resolution, spectral resolution, and temporal resolution. Spatial resolution is the size of the ground detail. For example, 10 meters means each pixel roughly covers a 10 by 10 meter square. Spectral resolution describes how many and which wavelength bands the sensor captures. Temporal resolution, or revisit time, is how often a satellite can image the same place. Together these determine what each satellite is best suited for. Over time, we can assemble a time series, stacks of images of the same place over weeks, months, or decades. That temporal depth is what makes satellites so powerful. Change detection, trend analysis, early warning, and long-term monitoring. Landsat 8 and Landsat 9, the long record of Earth. Imaging: 7 o'clock to 15 o'clock, 8 o'clock. Intro and historical context: 7 o'clock to 8 o'clock. Landsat is the world's longest continuous record of Earth observation. With origins in the 1970s, Landsat satellites have produced a global, multi-decadal archive that is invaluable for science, land management, and environmental policy. Landsat 8 and Landsat 9 continue that legacy by providing consistent, calibrated multispectral data of the land surface, enabling direct comparisons with images taken decades earlier. Instruments and capabilities: 8 o'clock to 11 o'clock. Landsat 8 and Landsat 9 carry 2 primary instruments. First, the Operational Land Imager, OLI, captures multispectral visible, near-infrared, and shortwave infrared bands. These bands include the blue, green, and red channels needed for natural color images, as well as near-infrared for vegetation, and several shortwave infrared bands, which are valuable for distinguishing soil and moisture, and for cloud detection. OLI also includes a coastal aerosol band, useful for shallow water and coastal studies. Second, the thermal infrared sensor TIRS measures thermal infrared radiation, recording surface temperature. TIRS is essential for studies of evapotranspiration, urban heat islands, and wildfire monitoring, because Landsat provides both multispectral and thermal measurements on the same platform. It's uniquely useful for mapping land cover and also understanding energy and water fluxes. Landsat's spatial resolution balances coverage and detail. The multispectral bands are typically 30 meters per pixel, while thermal bands are coarser, often 100 meters or so, resampled to 30 meters in many products. But it's the long record, consistent calibration, and data continuity that gives Landsat special value. Products and applications, 11 o'clock to 14 o'clock. What do people do with Landsat data? There are countless applications. Urban planners use Landsat to map urban expansion and impervious surfaces. Forestry agencies track deforestation and forest regrowth. Hydrologists estimate surface water extent and monitor reservoirs. Agricultural analysts use spectral indices like the Normalized Difference Vegetation Index (NDVI) to infer vegetation health and crop vigor. Landsat thermal data supports drought monitoring and irrigation planning by allowing calculation of EVAPO, TRAN, SPIRATION, because historical Landsat archives go back decades. Researchers use Landsat to reconstruct long-term land cover changes, the spread of farmland, the retreat of glaciers, coastal change, and long-term urbanization patterns. Strengths, limitations and tips for narrators 14 o'clock to 15 o'clock. When narrating scenes about Landsat, emphasize its continuity, the 30-meter sweet spot that balances archive and detail, and its role as a scientific backbone for long-term land change studies. Also note limitations. Landsat optical sensors cannot see through clouds, so analyzes over cloudy regions require compositing multiple images or using radar. Complements, asterisk, the Sentinel family. 15 o'clock to 29 minutes and 0 seconds. Las 2 de la tarde total. Asterisk intro to the Copernicus Sentinels. 15 o'clock to 16 o'clock. Europe's Copernicus program provides free, open, and regular environmental data from a suite of Sentinel satellites. Each Sentinel mission is designed for specific measurements, and together they create a flexible, operational system for environmental monitoring, agriculture, water, emergency response, maritime surveillance, and climate services. Sentinel-1 radar for day-night, all-weather imaging. 16 o'clock to 2034, 30 Sentinel-1 is an active radar mission using synthetic aperture radar SAR. Unlike optical image, radar sends microwaves to the ground and measures the returned echo, which means it can image day or night and penetrate clouds and rain. Sentinel-1 data are extremely valuable for monitoring surface motion, mapping floods under cloud cover, detecting ships at sea, and mapping sea ice and oil slicks. Key strengths of SAR include sensitivity to surface roughness and structure, making SAR ideal for detecting subtle ground deformation from earthquakes, landslides or subsidence, when images are compared over time using interferometric techniques. For coastal and flood monitoring, Sentinel-1's ability to see through clouds is a major advantage during storms when optical sensors are blind. Common uses: interferometric synthetic aperture radar, NSAR, to map millimeter to centimeter scale ground motion, flood mapping during emergency response, ship detection and maritime surveillance, and monitoring of Arctic sea ice, extent, and dynamics. When describing Sentinel-1 on camera, show SAR images side by side with optical imagery to illustrate how textures and structures show up differently. Waves, ships, city layouts and flooded areas all have distinct radar signatures. Sentinel-2, higher resolution optical multispectral imaging, 20:30 to 25 minutes and 0 seconds for 30 Sentinel-2, provides high-resolution optical imagery in visible, near-infrared, and shortwave infrared bands. Its spatial resolution is finer than many global sensors, with 10 and 20-meter bands, and its spectral set includes bands specifically designed for vegetation monitoring, watercolor studies, and soil and snow discrimination. The twin Sentinel-2 satellites increase revisit frequency, giving images every few days at mid. That temporal density makes the mission powerful for monitoring agriculture throughout a growing season, detecting rapid land use change, mapping burned areas after fires, and generating cloud-free mosaics with high temporal fidelity. Key products: multispectral scenes, NDVI time series for crop monitoring, and atmospheric correction products for scientific use. Because Sentinel-2 is optical, it's limited by clouds, but its frequent revisit helps build cloud-free composites quickly. For narration, emphasize Sentinel-2's role in operational land monitoring, near real-time, agricultural and vegetation monitoring, and its usefulness for higher detail mapping compared to coarser sensors. Terra, NASA's multi-sensor climate and earth science observatory, 29 minutes and 30 seconds, -35 to 36 o'clock. Terra is a cornerstone NASA mission that carries a suite of instruments to study Earth's climate system, atmosphere, land, and ocean interactions. It was designed as a multi-instrument platform to gather broad range of measurements about the planet at once. Instruments and mission goals: 29 minutes and 30 seconds to 32 minutes and 0 seconds. Terra's instrument suite includes imaging and radiometric sensors that monitor clouds, aerosols, land cover, surface temperature, and vegetation. These instruments include multispectral imagers and moderate-resolution radiometers, which provide frequent, global coverage. Terra's measurements feed into climate models and global environmental analyses. One of Terra's most widely known instruments provides daily moderate-resolution imagery, useful for tracking large-scale phenomena like vegetation cycles, wildfire plumes, dust storms, and volcanic emissions. Together, the instruments let scientists quantify how energy and materials flow through the Earth system. Applications and long-term value: 32 minutes and 0 seconds to 34 minutes and 30 seconds. Terra's global records are central to climate research, observing seasonal cycles of vegetation and snow, tracking aerosol transport from dust and fires, monitoring cloud properties and radiation budgets, and informing climate model validation. Terra's data are also used operationally. For example, large fire detection and mapping, air quality assessments, and large-scale land surface monitoring. Because Terra's observations are co-located in time, multiple instruments observing the same place within a short period, researchers can combine measurements from different sensors to study relationships between land surface reflectance, energy fluxes, and atmospheric composition. Narration tips: 34 minutes and 30 seconds, -35 to 30, when presenting Terra. Highlight its role as a systems observatory, not just an imager, but a platform that measures multiple Earth system variables simultaneously, and how that integrates into climate science and global monitoring. Cartosat 2 series, high-resolution mapping from India. 35 minutes and 30 seconds to 42 minutes and 30 seconds, 7 o'clock. Cartosat 2 series satellites are India's higher-resolution remote sensing workhorses focused on cartography, urban planning, infrastructure, and surveillance. They produce panchromatic and multispectral data at high spatial resolution, making them well-suited for mapping cities, transportation networks, and small-scale land use features, capabilities and typical uses. 35 minutes and 30 seconds to 38 minutes and 30 seconds. Cartosat 2 satellites typically provide very high spatial resolution, panchromatic imagery, and accompanying multispectral data, with resolutions on the order of a single few meters. In panchromatic mode, Cartosat imagery supports detailed mapping, resource management, and infrastructure monitoring. Applications include urban planning, disaster response for high detail, situational awareness, precision mapping, and support to national mapping agencies. Cartosat's high resolution is especially valuable in contexts where fine spatial detail matters: mapping building footprints, road networks, small water bodies, and ports. The Cartosat 2 series operates with a flexible imaging schedule to support government and commercial tasks. Examples in case studies: 38 to 30 -41 to 30. Practical examples include rapidly generating updated urban maps to inform zoning and infrastructure planning, mapping damage after an earthquake or cyclone to help responders prioritize areas for rescue and aid, and monitoring coastal infrastructure, ports, and harbors. Cartosat's data are also used in precision agriculture and forestry when very fine detail is required. Caveats and operational considerations. 41, 30, -42 e 30. High spatial resolution often means narrower swath widths and less frequent revisit for any single satellite. For operational monitoring, Cartosat data are often combined with wider coverage missions, like Landsat or Sentinel, to provide context, and then used for detailed follow-up mapping, cross-comparisons, applications, and real-world examples. 42 minutes and 30 seconds, to 47 minutes and 30 seconds. 5 o'clock now. Let's compare and synthesize. When would you use which satellite? For long-term land cover change and a consistent archive, Landsat's decades of calibrated data are unmatched. Use Landsat for trend detection, glacier retreat studies, and urban expansion over decades for frequent high-resolution optical monitoring. Sentinel-2 provides rapid revisit and fine spectral bands useful in agriculture and timely vegetation assessment for all weather, day-night monitoring and deformation studies. Sentinel-1's radar is indispensable during storms and for ISRO deformation maps after earthquakes or for subsidence monitoring in cities, for ocean and climate fields requiring stable radiometry. Sentinel-3 and Terra provide the radiometric consistency necessary for sea surface temperature, ocean color, and atmospheric studies. For very fine detail mapping and infrastructure, Cartosat 2 series offers panchromatic detail used in mapping, urban planning, and disaster aftermath assessment. Example scenario: flood response. Imagine a major flood event. Within hours, Sentinel-1 can deliver radar images that map inundation, even under cloud and rain, critical for directing rescue and relief. Sentinel-2 and Landsat provide optical views when the weather clears for damage assessment and mapping land cover changes. Cartosat can then supply higher resolution imagery to plan local reconstruction or inspect critical infrastructure. Terra and Sentinel-3 contribute broader environmental context, like regional precipitation patterns and sea surface conditions, which help with forecasting and relief logistics. Example scenario: agriculture monitoring for seasonal crop monitoring. Sentinel-2's frequent multispectral images enable crop type mapping and stress detection across growing seasons. Landsat's long record supports historical baselines and yield trend analysis. High-resolution Cartosat images can be used in demonstration plots or precision agriculture where field-level detail is needed. Combined, these systems support food security and market forecasting. Future directions, challenges, and ethics. 47 to 30. 50 minutes and 0 seconds. 3 o'clock. As we look ahead, Earth observation is becoming faster, denser, and more integrated. Constellations of small satellites are increasing revisit frequency and expanding the range of available spatial resolutions. Cloud computing and machine learning allow near real-time processing of massive archives. At the same time, important challenges remain: ensuring data continuity, maintaining calibration to enable long-term climate records, handling enormous data volumes, and addressing privacy and data governance concerns as high-resolution imaging becomes more widely available. Ethical use and open access policies matter. Publicly funded missions, by providing open data, support scientific research and humanitarian applications. But with higher resolution and frequent revisit, societies must also discuss rules around privacy, responsible surveillance, and transparent governance. Closing sign-off. 50 minutes and 0 seconds. Short, warm conclusion. That brings our tours to a close. We've explored the long legacy of Landsat, the operational power of the Sentinel family, the climate-focused insights from Terra, and the detailed mapping capabilities of the Cartosat 2 series. Each satellite brings unique strengths together. They provide the rich, multi-scale view we need to monitor, understand, and manage our changing planet. Asterisk.